Hi, this is Laura Case, and I'm here with Mike Barcik.
Hi, Laura.
Hi, Mike. We're going to talk to you today about commercial envelope energy code and plenum returns. I am a civil engineer with a lot of building construction and management background, as well as I'm a lead fellow and a lead AP in building design and construction.
And I'm a mechanical engineer and a technical principal here at Southface, and I get to do a lot of work with our education efforts, particularly wrapped around energy codes. And we're going to talk about a very specific part of the energy code today, which is doesn't actually say the word plenum returns on here, but we're going to talk about plenum returns and versus ducted returns.
Right.
And I think you'll pick up on some bias from us as we go through. That was interesting. Our presentation kind of ran away, but now it's back.
Yay.
So a couple great resources. And I should mention that it's now January of 2020 as we record this. And Georgia is on to its latest energy code. The 2020 Georgia Energy Code is actually based on the IECC 2015. And whenever you adopt the IECC, you inherently also get an ASHRAE 90.1. And the version of 90.1 is 2013. So really, in Georgia, you can use either commercial energy code.
Okay, good to know.
The only rule is when you pick one code, you have to stay with it for everything. So you can't like do, envelope under IECC and lighting and mechanical under ASHRAE 90.1. You have to be consistent. So okay. That's one thing to do. They're fairly comparable, but we're and we try to be code neutral here, and particularly on this topic, you'll see that you're allowed to do ducted or unducted returns in both codes, and we're going to talk about sort of the performance aspects of each.
Right.
I want to make a pitch too, Laura, for our website, southface.org. At Southface, we have a shortcut now to get to some of these great Georgia Energy Code resources, and there you can see it's just resources, and then it'll offer you a list. There are some webinars, which is probably where you found this one. There are a bunch of tools you can download. There's a commercial field guide, which I think is a pictorial user's guide to the energy code. There are slides for the long presentations, and there's shorter webinars on smaller subtopics. So hopefully you'll find that interesting. Can you tell us about that last link down there, Earthcraft?
Sure. Earthcraft is one of our own programs for sustainability in residential, multifamily, and small commercial buildings. We fashioned it as a certification specifically for Southeast moisture and heat issues, as well as a certification for small commercial buildings, because we felt like that was a needed gap in the market.
And we say small, but I think, we've got projects that are pushing 50,000 square feet. So it's really more, I always kind of say it's for more simple, straightforward, like we're not really necessarily trying to go after a big building with chiller and, cooling tower and stuff like that. We're trying to focus on buildings that sort of make sense, and like you said, often are ignored. So, and it's going to make it exceed the energy code, and that's a good thing in itself. Kind of guarantee performance for the occupants. So Earthcraft, a lot of people know it from the house program, that program has been around for over 20 years now. So, and the commercial program, I think, has been around for at least a decade. So anyway, let's drive on. And Laura, a little bit more about Southface real quick.
Sure. Southface is a nonprofit organization. We've been around over 35 years now.
Make that
40.
40 plus years.
Yeah, 40 plus years. That's right.
It was 1978. So
wow.
42 now.
42 years. So our goal is to build a regenerative economy, responsible resource use, and social equity through a healthy built environment for all. And the photograph shows our two buildings. One was built in 1996, around then, as an example of how you can take off-the-shelf products to build a sustainable building. And then to the right is the Eco Office that was built approximately 10 years later. And it is also an example of a high-efficiency, high-performance building. And it's a LEED Platinum, also Earthcraft Light Commercial Platinum, Energy Star.
You name it.
You name it. We got that
good bells and
certification.
whistles,
That's right.
Yeah, that's it. Cool.
Yeah.
And so, I guess today we're just going to kind of elaborate a little bit more on some of the air sealing details about the thermal envelope, touch a little bit on some of the roof insulation details. But like I said, mainly those tie into the main topic we want to cover, which is discussion of a ducted return versus using the plenum space as a return. So in terms of establishing the envelope, one thing that's interesting to note is that both codes have this language which is nearly identical, that basically say the designer has to identify what are the air barrier materials, and those have to be spelled out in the CDs. So they have this interesting list of, and there's one or two things that don't quite line up between the two codes, but they're really close. So it's kind of funny in that regard. But they list materials which they deem essentially viable or worthy as an air barrier, exactly. Right. Which is somewhat naive, because our experience is, yeah, it's true, and probably you're going to be building with one of these many materials that are listed here, but it's really, that's not where the failure, the leakage doesn't occur in the middle of a piece of OSB. No. It occurs at the penetration or at the seams, that kind of stuff.
Exactly.
So that is very specifically spelled out, that joints, intersections, penetrations have to be detailed and air sealed, and that the air barrier has to be continuous, and it has to be, like we say, if you took your pen on the drawing and you stuck it and you trace the air barrier, you need to be able to draw all the way around without lifting your pen up, because the air barrier needs to be continuous. So it's about identifying, and sometimes it's more than one type of material that makes it up. But I always like to say you need to identify the primary air barrier. And for example, in exterior walls on new construction, that's usually the sheathing. Make the sheathing tight, and your walls are going to be tight. And then we'll talk a little bit about roofs. And a lot of times we see slab foundations, so the slab can be pretty tight. But again, those are in themselves fine. It's the penetrations through those. It's the seams and the gaps and the junctions. That's where the failures occur. So we'll keep re-emphasizing that. But it all starts with, I guess, picking one of these magic materials that somehow works out.
That's right.
Okay.
So air barrier air insulation has to be wrapped, sealed, caulked, gasketed, or taped. So that includes doors, door frames, junctions between walls, and roofs, foundations, building corners. So anywhere where there is anywhere where there's a connection, a floor and a wall, or a wall and a roof, anywhere there are these connections or penetrations. So we want to talk about, building assemblies used for ducts or plenums, and also anywhere there's a joint, a connection between planes, a seam, or other changes in the continuous air barrier material.
And I just think it's interesting that these are all places that the code specifically, explicitly spells out as you need to air seal these. And one of them is if you're going to try to use an assembly as a plenum, that is specifically spelled out. But again, this is our whole issue, is that often that isn't done well. And even if it maybe was done during construction, it often gets violated over the life of that building. So again, a teaser for what's coming. Laura, this is interesting. We were involved in some research on light commercial buildings under 50,000 square feet. And initially, we looked at about a dozen smaller commercial buildings, and we blower door tested them. And at the time, and probably even today, there just have not been that many commercial buildings that have been blower door tested. That number grows every year, but I would just guess at the time we were doing this, probably not even 1,000 commercial buildings had been blower door tested, and whereas millions of houses have been tested.
Right.
And so one of the questions that came up was, we had a sense of what a good tight building would look like, one that was sort of trying to be paying attention to air sealing details and knowing that they were going to have to pass a leakage test. So the question that came up was, well, how bad or how good is an average building? And that was the interesting thing. So, is a building that you're trying to pay attention to air sealing, how much tighter is it? Is it 50% tighter? Is it 100% tighter? And the answer was what?
3 times tighter.
Yeah, we actually saw that ratio for the first dozen buildings, but then we ended up testing about 50 or really more than 50 buildings. And that continued to play out. It's even at the end, it was about a 3 times factor between buildings that were trying to be, pay attention to air sealing, knew they had to pass a test, versus ones that were, let's just say, standard construction or existing buildings.
Right.
And so it was also quite the spread. And if I remember too, we found that there wasn't really a correlation like with the age of the building. We found new buildings that were unbelievably leaky. We found old buildings that were unbelievably leaky. We found new buildings that were tight, and we found old buildings that were tight. So, and you couldn't really say that it was, oh, this is a block building, it's going to be tight, or this is, So it wasn't a material connection. Although I think we'll see it in a case study. I think we did find that corrugated metal roofs often presented a challenge.
Yes.
So we'll tease you more with that.
That's my experience.
Yeah, but a lot of, I don't know how many buildings we've tested to date, but over 50 for sure. And then now we're going to dive into this specific topic. So Laura, can you kind of briefly just lay out here, what is this? What does this mean, a return plenum?
Right. So if you picture in your mind your standard small commercial building, maybe,
or even a large commercial building.
Yeah, or even
matter.
large, right. And so you usually have, even if it's either a hard lid ceiling that's sheetrock, or you have, even more typical as seeing a lay-in ceiling, with a grid. All that space above the ceiling oftentimes is used for your return air plenum. So the air that's going back to the air handler to get warmed or cooled is flowing through this plenum, right?
Yep.
So that would be non-ducted, and ducted would mean you had a ducted path, right? The air would flow through ductwork.
Right.
So that's the difference.
And so to be fair, we look at, we'll try to present all sides of this argument. The argument that if we don't run actual ductwork, that we can sort of value engineer out the cost of those return ducts. Generally, you don't have as much return duct area as you do supplies, but that they're claiming that could be 10, 15, 20% of the HVAC system cost, because you're eliminating the cost of that ductwork. Right. And what's the second bullet?
So you're not coordinating ductwork going alongside other overhead utilities such as sprinkler systems, your supply ducts, whatever else might be.
IT cabling.
Yeah, IT cabling, whatever you want to stuff in your ceiling. Above your ceiling, right?
So the idea that we aren't running a duct, or it's one less duct that we have to run, so it doesn't get in the way of other stuff.
Right. And
this last bullet, so there's some Benjamins over here floating around to represent the savings, and we'll come back to him. But the idea is we're assuming that the cost of the operating the fan system is going to be reduced because, you're getting a lot of return area, and so it's low pressure drop, and that's lower fan energy. And to some extent, I think that's true. But I would argue that it's not necessarily an apples to oranges comparison. That I think one of the challenges with using plenums is that the air doesn't necessarily come from where you think it does.
Right.
Whereas with ducts, you have a better chance of kind of knowing that the air is making its way back through those ducts.
Right.
You may end up, and again, if a proper test and balance is done, that can help to offset that. But you may not really be pulling air from the place that you thought you were. And I think that that a lot of times is we've definitely seen examples of that sort of create some failures in commercial buildings too. So, again, I think there's sort of the theoretical savings, but then there's also the does it really perform on par? And in my opinion, the answer is no. Here is an anatomy of a section of a building. This is one of many buildings that I have personally seen that had a problem, and this particular one was a car dealership, and it had a rooftop, unit, and the supplies that kind of went through that plenum space, and the above the drop ceiling was, the return air plenum, and the light fixtures were ventilated. There were probably some openings to allow air to get back up there, but the challenge was that the wall, the exterior wall, and actually also the wall over here, this interior wall that went to another space, when you pushed the drop ceiling tile aside and you looked out, it actually did not seal to the top. In other words, you really didn't have a plenum.
No.
The plenum in this case was inadvertently extended out to include this big overhang. And it's very common in a commercial building. I personally have found this in multiple buildings. Whenever there's any kind of an attached, like tuck under, a porte-cochere kind of thing, like a motel might have, or the entryway of a building, that very commonly that this wall sort of stops just above the visual line. And no one ever sees it, so who cares? Right. Except when you make it into a plenum, now it's under pretty decent negative pressure. Right. And often this part is not airtight. There's light fixtures out here and so on. And so what ends up happening is, you end up air conditioning Atlanta or whatever city this is located in. And that's a real problem. And this is a great pathway for tons of humidity to get in, to really be sucked in. Well, and also, like, if this was a school or some sort of drop-off for children, you've got idling cars. Or school buses. Or, even better. Or stinkier. So you're pulling in all this polluted outside air. So that's another, it's amazing how common this problem is, or this type of an issue is. And it really kind of comes down to, when you don't have a dedicated material or a ducted material as a duct, then it often gets violated. And it may be that it was, even if it was built perfectly in the very beginning, it still gets violated over time. In this particular car dealership, there were all kinds of leaks at the top, but there was actually a giant hole that had been smashed. And it was because an electrician had come out and replaced the light fixtures out here. And so it left a 3x4 opening in that. So it was already connected because, and a lot of times too, if the roof is a waffle roof deck and the wall is a steel plate, it doesn't meet, and no one ever sees it. No one's ever going to see that. And then it was ironic because on this side there was leakage also, and it connected to an interior space, but it happened to be where they were storing car parts and they were actually working on cars. Oh, wow. So there was like a little bit of risk of carbon monoxide and things like that being pulled in. So that was one classic example. Okay. You want to take this? Sure. So even in the best buildings, when they're freshly done and they've been inspected and they're all air sealed and tight, at some point in time, especially where equipment tunnels and chases are involved, like for the top right, there's all those electrical conduits going through the wall. Somebody's going to
take out some block or, just put a hole in the wall, right? So you have no control over that once the building's in operation. And as Mike said before, these are highly depressurized. So they're pulling in air from wherever they can get it. And so the air comes in from everywhere and anywhere.
Yeah,
so,
this is another, the top picture is another commercial building I went to, which showed, had a, I think it was even kind of a built into the side of the grade, and I want to say it was a vented crawl space on the other side of that.
Okay.
So here, someone had to run maybe a refrigerant line.
Mm-hmm.
That's kind of what that looks like.
Right.
And so they ran that refrigerant line, through this wall. They busted out the bricks. No one's ever going to see it, but on the other side of that wall is a vented crawl space, and it was moldy in there. Mm-hmm. So what you're sucking in humidity, you're sucking in mold from the vented crawl space into this commercial building, which was obviously more than one story. I did want to show a picture of it having been done right. So, this is a case where fire code actually kicked in and they did actually seal the penetrations. But that's kind of uncommon.
Right.
The other thing is that I think a lot of people, when they go into a commercial building, I think almost any person on the planet has been in a commercial building and seen water stains on the drop ceiling.
Yep.
I don't think anybody's never seen that. And so that's a fairly common occurrence. And 99 out of 100 times, that is not a roof leak or a plumbing leak. And Laura, what is that? What's the source of that?
Well, I would suspect since you look through the glass window and there's this downlight outside,
yeah,
right?
A hole.
Yeah, there's a hole basically, and
so
negative pressure pulling in hot, humid outside air. Yeah. It hit something cold and possibly metallic, like I don't know, pipe.
Sprinkler pipe, anything. Who knows?
Who knows? But it's hitting this cold.
Duct.
Yeah, it's hitting this cold metallic object, and it's raining condensation. So yeah.
And a lot of times too, you'll see here. You can actually see the water stain, but you can also notice the ceiling tiles are kind of saturated and they're sagging. Mm-hmm. That's another indication that there's a moisture. Some of these kind of a poker term is there's a tell, there's something that kind of reveals there's a problem here. And that's a classic example. So again, this was a spec office building that, could be located anywhere in the country, right. and just had that, a certain amount of overhang and a leak path. One thing is that the code kind of says if you're going to do ductwork in an unconditioned space, it has to be insulated. If it's outside the envelope, like in an attic or, along the top of the building, then it has to be R8. And they actually say, the code says if you run ducts through the inside of a building, they don't have to be insulated. Now, we would always recommend, like a supply duct would always want to be insulated to prevent condensation or sweating on it. But if you're actually using part of the building, the duct itself has to be, if you're using the building as a duct, the minimum R value has to be R8. And actually, ironically enough, if you take, pretty inexpensive construction, steel stud, 16-inch on center, 2x4, somebody puts an R13 bat in there, that actually effectively is only an R6. So you're not even meeting that capability. And it's another concern. Right. I don't know that that's the major issue. I think it's really more about leakage, but R value is a factor. And Laura?
Yes, you shall not put per code. Yes. If you put insulation above a ceiling, I hope you're doing it for sound insulation because it won't contribute to your insulation value of your roof. So
yeah, it's very explicit. This has been in the code. It's actually been in ASHRAE 90.1 since the 1999 version. They specifically, explicitly spelled it out, and the IECC a couple years later spelled that out too. And now it used to be kind of implied, but now it's actually stated you cannot do this and count it as part of your envelope. You can do it for acoustic reasons, but that has its own set of issues.
Right.
So this is not an acceptable way to essentially comply with energy code in terms of meeting the R value requirements for the ceiling.
Right. And Mike, I think you and I have both seen where you pop a ceiling tile and it looks kind of like that. Yeah.
Yeah.
It's just a mess.
And it doesn't get better with age.
No.
And a lot of times the fiberglass particles become more airborne over time, and that actually is an air quality concern.
Right.
Or it's just particulates in general. But even if this was done correctly, which it can't be, it often gets moved around.
Right.
And it's not airtight. I mean, you've got 8 feet of crack for every one of these single drop ceiling tiles, and you got ventilated light fixtures and so on. So
Right.
it's just it doesn't meet the definition of thermal envelope. So a way that is allowed is to put a hard air barrier and then insulation on top of that, kind of like an attic assembly. It's got its set of issues too.
Right.
And very often this is hidden and therefore gets violated. Somebody will poke a hole through that ceiling as well as that wall because it's all hidden.
Right.
I would say too, Laura, this reminds me that I like the cloud approach. That's an architectural term where they don't run the drop ceiling all the way to the edge. They actually float the ceiling grid system with a, say, 2 or 4 feet from the edge. You can actually look up and you can see. And it's funny, I just think it keeps everybody honest.
Yeah.
And any holes up there now would be quite evident. And somehow it just seems to work better. So I think if you're going to do a cloud ceiling, that has a better track record. You are, in some cases, particularly as a retrofit, you can spray foam up against the underneath of the roof deck. That foam would most likely have to be coated with an intumescent coating as a thermal fire barrier kind of thing. But again, this is better because it probably won't fall off and you can't really poke a hole, but the wall is still subject to it. Arguably the best place for roof insulation is continuous above the roof deck.
Right.
And we want that to happen. We're still saying, though, that we think this should be a ducted return instead of trying to use this as the plenum, just, again, because of the real world.
Right.
This is a new one, though. This is kind of interesting.
So, yeah, I'm just kind of reinforce the importance of ducted returns. So hospitals and outpatient facilities, et cetera, and adopted these facilities guidelines by the Facility Guidelines Institute in 2018. And they require ducted returns in many of the healthcare-related facilities. And it's primarily due to the spread of infection. So that is another concern. You want to have a healthy building. So ducted returns actually...
Again, you know where the air is coming from.
Exactly. And you're controlling it.
And you're able to manage it a lot better when it's ducted. Otherwise, it's kind of a sort of more wing and a prayer return path. And so I think that's really compelling, though, and that's pretty new. That I had not heard of that until recently. And so to kind of wrap us up, a couple case studies that I think we tested some buildings. This was a dining facility, if I remember right.
Dining facility.
And initially, the thing we're blower door testing. In this case, we're pressurizing the building, and that is supposed to be the return plenum space above there. And obviously, if it was airtight, when we blew air into the building, that fog would not be racing up in there the way it is. But you can see it clearly was not airtight.
Right.
And there's a lot more going on in that building, but that was one particular, kind of a particular issue that it had. This is another one that we also tested. This is an interesting one. We tested the older part of this was a school, and it had kind of an attic space it was a flat roof, but it basically had a flat ceiling with an attic space below the flat roof, and it was vented. And we removed all the old insulation. We did not vent it anymore. And all of a sudden that building got significantly tighter. We really improved our air sealing dramatically. This part was actually the newer wing, which was built probably in the, I think in the mid 90s. And what you're able to see, or this particular one had split systems. So you see the packaged outdoor units. Those inlets above the windows are the ventilation air, the outside air that's supplied. And you can see the impact. That was the inside of one of those windows. And that was the failure that was occurring. Again, we're using a plenum space as a return. The outside air was ducted through that. It had issues with air leaking in, hitting a cold surface, and you could absolutely see it right there. So, you know, when the weather conditions are right, let's say it's October and you get some of those first cold nights where there's still a fair amount of humidity in the building, but you start bringing in outside air and it's cold. So that duct is cold. So all the humidity around it, that outside air duct is above that drop ceiling tile.
Right.
It dripped and dripped and dripped. And you can see the sagging of the other tiles too.
Definitely.
So, good example. And then Laura, this was another one that we went to that was, it had a big gymnasium attached to a bunch of classrooms. And this one just had no defined air barrier at all. They had a mechanical closet with louver doors, and that closet was in no way sectioned off from the rest of the building. So basically you had this easy pathway for outside air to come in here, and then there was no barrier, no separation. Yeah. So that outside air just comes in, and then it gets into the space that it's effectively a return plenum. So it's drawn in by the return, lack of return ducts and so on. So no clear air barrier, no clear return pathway, and faith-based ventilation. Sometimes I think we call that. But this was what you'd see from the inside of that mechanical closet, and you can see there was no ceiling whatsoever. And those louver doors, which are in horrible condition, were there to provide combustion air for this equipment, but that was not intended to let it leak right in.
So you have outside air coming through a mechanical room that has combustion equipment that's not sealed off.
Right. Room is not sealed off.
Right. And the room's not sealed off. So you have whatever exhaust air is coming out of the combustion equipment going into the building.
Well, just a lot of bad design efforts here. And here's what it looked like from the inside. And I think they had a contest to try to paint over the water stains, it seems like. So, but again, that was the saggy tiles with the drops on them. That's all evidence of a return pathway that's not been defined, and a poor air barrier too. So Laura, hopefully we've made a case for our opinion on this, which I feel is pretty clear. Our friend Ben Franklin says, well, you might save a little bit of money in the short term, but in the long term, you really regret the decision, and the bitterness of poor quality remains long after the sweetness of low price is forgotten. So again, I think, any concluding remarks?
Well, the cost, I would say the cost, there's a perceived cost add. I know there's a little bit more effort to put in, a coordination effort and to design ductwork well, right?
What a concept, designing the ductwork.
Exactly.
And actually, that's a good point. I think that actually when you have a ducted return, it forces your hand a little bit. You have to design the duct system.
Right.
And that in itself, I think, is a positive thing that offers additional benefits. So it's kind of the real world meeting, the ideal world to some extent here. But hopefully people have gathered our opinion on this particular topic. So, well, with that, I think we're going to say thank you.
Thank you.
And we'll call it a day.